Hello, Physics Nation. My name is Nate Larmond, and this is my second video on significant figures. I like to do a handwritten solution as well as sort of an on-screen drawing solution. I think this provides a little more freedom. It's just, pen on paper. Anyway, same old rules. All non-zero digits are significant. So in 14,000, there are two significant figures. And the last one to the right here is in the thousands position. So this range of uncertainty is plus or minus 1,000. You just bump up and bump down the last number to the right. This is the last significant figure. Could be as big as 15,000 or as small as 13,000. So how about rule number 2? Well, the zeros are the annoying rules. If they're in between two significant figures, they're significant. So 0.205 has three significant figures, and the uncertain place value, again, is on the far right. It's in the thousandths position this time. Tenths, hundredths, thousandths. You have to say the TH very clearly. Thousands position is obviously big, like 3,000, 4,000. We're talking about the thousandths position. So, I don't know, for a thousandth of a gram, you would need a very fancy electronic scale. Most mechanical triple beams do not go to the thousandth of a gram. Anyway, as you can see, real tight range of uncertainty. You just push it up by 1 or down by 1, 0.206 or 0.204. A range of uncertainty of 1/1000th of a gram. Very precise. How about another zero rule? If the zero is to the right of the decimal and to the right of the numbers, that's a significant digit. So 0.10 has two significant figures. This 0 is significant because it's to the right of the decimal and to the right of the numbers. That is, you push it up by 1, 0.11, 11 hundredths, or you push it down by 1, 0.09, 9 hundredths. The range of uncertainty here is a hundredth, but perhaps a different way to look at range of uncertainty is you do the uncertainty divided by the measurement itself. It's called percentage uncertainty. So, it all depends on the context. Plus or minus a hundredth could be great if you're talking about runners moving over 100 meters. If you could measure that time to the hundredth of a second, that would be amazing. But if you're trying to measure how quickly something falls over a short distance, it's not so amazing because the measurement itself is 10 times the uncertainty, or the uncertainty is 1/10 of the measurement itself. Anyway, that's called percentage uncertainty, and that's kind of rough. 10% is, a sloppy range of uncertainty. The truth is varying a lot within your measurement. And here we get even worse. So zeros on the right-hand side of the decimal, but left-hand side of the numbers are not significant. 0.05 only has one significant figure, the 5. So now it's still plus or minus a hundredth of a second, but now the measurement itself is half as big. So 1 out of 5 hundredths is 20% uncertainty. Okay, so 0.05 could be as big as 0.06 or as small as 0.04. The truth is plus or minus 20% of the measurement you are trying to make. That's pretty uncertain. And here we go with Jeff Bezos, the richest man on Earth. Oh, is he worth, I don't know, 113 billion? Well, whatever. Amazon just keeps going up and up, so he'll be worth 140 billion by the end of the week. Here's the crazy thing. Scientific notation is obviously better than writing 9 zeros. So 113 times 10 to the 9th could be as big as 114 billion or as small as 112 billion. Jeff Bezos, like I said earlier, looks at the stock market and, makes $200 million and then loses $400 million and then makes $500 million. So technically speaking, his range of uncertainty is 1 billion. All of these zeros are described as placeholding zeros, which sounds crazy uncertain, but 1 out of 113 is actually a small percentage uncertainty. Now we're less than 1%. So it sounds like his net worth is just on this roller coaster ride, but it's not. It's only bouncing around by less than 1% of the entire amount. So small percentage uncertainty. And imagine he gives you $10,000 for your birthday. Well, 113 billion minus 10,000 is 112,999,990,000, right? Well, wrong. See, in the world of science, 113 billion's range of uncertainty is so huge, that is 1 billion, plus or minus 1 billion, that subtracting 10,000 has no effect on it whatsoever. It's like a drop in the bucket. Or I say it's like you standing on a bathroom scale and then spitting. See, the bathroom scale is plus or minus a kilo, and your spit is maybe a gram. So did you lose mass? You did. However, it's 1/1000th of the range of uncertainty of the tool. So the tool is not going to notice any difference, even though you did lose a small amount of mass. It's within the range of uncertainty of the tool. You're just squishing a stiff spring, and that spring is attached to a gear system that turns the dial. Anyway, is that the end? No. Okay, so the last rule is for multiplication and division. Here, you don't worry about place value like addition and subtraction. Here, you count the number of significant figures. So we usually find the volume of your tabletop. It's 60.2 centimeters wide, 183 centimeters long, and 2.5 centimeters thick. If you hit the buttons on the calculator and just do thickness times width times length, you'll get 27,541.5. But that is wrong in the world of significant figures because it implies a range of uncertainty that's unrealistic. There's uncertainty in this tool right here, this ruler. So if this number is, plus or minus a millimeter, and this number is plus or minus a centimeter, and this number is plus or minus a millimeter, there's actually a really wide range of uncertainty because, well, it's, a dimension multiplied by a dimension multiplied by a dimension. So tiny uncertainties propagate to the calculated value. That's the fancy name for how sloppiness in a measurement becomes sloppiness in a calculation. Waves propagate. So they say uncertainty propagates through calculated values. It's a simple trick. You just count the number of significant figures. 183 has 3, 60.2 has 3, 2.5 has 2. So when you're multiplying or dividing, you round the answer to the least precise number coming in. 2 is not as precise as 3, and so you have to cut off 27,541.5 to 2 significant figures. And, if the number is 5 through 9, you push it up. If the number to the right is 0 through 4, you leave it alone. This is 5, obviously, so we round that up to 28,000 cubic centimeters, plus or minus 1,000 cubic centimeters, which is kind of crazy. Your tabletop is roughly 28 liters, plus or minus a liter. That means it would take 14 2-liter soda bottles to fill your tabletop with water. An unusual result. This is one way to sort of prove why the range of uncertainty is so gigantic. So you can take each measurement and bump it up by 1 in the uncertain place value. 184 multiplied by 60.3 multiplied by 2.6, pardon my sloppiness. So if you push these 3 dimensions to their maximum on the highest part of the range of uncertainty, you could get as big as 28,848 cubic centimeters, or you push them all down by 182 multiplied by 60.1 multiplied by 2.4. You could get as small as 26,251. So notice a huge range. If all of these numbers skew big in the same direction and all of these numbers skew small in the same direction. And that is what significant figures mean. They are a measurement of uncertainty. Even if there is no range of uncertainty written next to the number, it is implied by the number of significant figures. Thanks for watching. See you in the next video.